In industrial lamination, the standard for structural integrity begins with the tooling. Premium press plates, like those engineered by Moldart India, form the baseline requirement for producing flawless panels at scale. Industrial lamination subjects materials to extreme heat and tonnage. Under these conditions, microscopic variances in raw inputs propagate outward, causing severe failures across the finished surface. Look at this exploded view of the press machine and panel. We are dealing with a tightly coupled lamination stack. The process requires exact synchronization across metallurgy, heat transfer mechanisms, substrate mechanics, and polymer phase changes. Achieving a zero-defect surface means passive tolerance management is mathematically insufficient. You have to actively reverse engineer every layer of this stack from its first principles.
The consequences of a poorly optimized stack are obvious on the factory floor: telegraphing and laking, surface steam blisters, and severe delamination. These visible errors are the macroscopic result of invisible microfailures buried deep within the tooling or the chemical composition of the inputs. During the press cycle, compressive loads and rapid thermal shocks search for the weakest link in the stack, forcing structural inconsistencies to the surface. To eliminate these defects permanently, engineers must mentally dismantle the press and rebuild it layer by layer, starting with the raw steel. The visual quality of any laminate begins with the stainless steel press plate. To maintain absolute rigidity under high pressure, industrial plates require an exact thickness ranging from 2.5 to 5.0 millimeters. This microscopic cross-section shows a hidden danger: the plate lamination defect. These are subsurface separations, pockets of sulfides and oxides, oriented strictly parallel to the surface. These structural weak points originate upstream. They are elongated inclusions, trapped and compressed during the initial hot rolling of the raw steel. Because they sit entirely below the surface, visual inspection is useless. Verifying zero-defect plate production requires deep acoustic profiling, using ultrasonic scanning or scanning acoustic microscopy. The tolerance limit is absolute. If the scan detects any internal discontinuities larger than 20 microns, the plate is rejected. The final decorative surface cannot compensate for poor tooling. Its structural integrity is entirely bound by the microscopic purity of the steel pressing it. Directly beneath the plate is the press pad. For decades, manufacturers relied on layers of craft paper to passively buffer the pressure. Today, that layer consists of highly engineered composite materials. This thermal map compares the uneven heat distribution of legacy materials on the left with the rapid, uniform thermal bloom of advanced pads on the right. By integrating woven copper filaments into reinforced silicone, pads like the Cardlam 230J11 actively conduct heat. That metallurgical integration yields a measurable operational advantage. Accelerating the heat transfer directly reduces cycle times, increasing total production output by 10 to 15%. More importantly, it eliminates surface defects. By providing precise, uniform pressure compensation across the entire panel, the copper silicone matrix stops the laking, frosting, and etch distortion caused by uneven thermal expansion. Optimizing this thermodynamic layer ensures the press pad actively regulates production speed and surface quality. The forces applied by the plate and pad eventually meet the substrate. This layer is highly susceptible to telegraphing, a mechanical failure where core irregularities transfer upward and permanently mar the decorative surface. This cross-section of medium-density fiberboard shows what happens when surface density drops below 750 kilograms per cubic meter. The highly porous core absorbs the resin, creating starved glue lines that inevitably lead to delamination. Beyond density, the materials operate within a strict moisture equilibrium window. Both the veneer and the underlying substrate must be locked exactly between 6 and 8% moisture content. Any deviation from that percentage induces failure. Too dry, and the panel warps from unbalanced hygroscopic stress. Too wet, and the high heat of the press flashes the trapped water into steam, blowing blisters straight through the surface. The core substrate must be mechanically and chemically perfected long before it encounters the heat and pressure of the lamination stack. The final active layer in this process is the melamine formaldehyde resin. Its ability to cure correctly is entirely dependent on the exact thermal transfer rates established by the tooling. This graph charts the 5-phase polycondensation cycle. The chemical evolution of the resin must follow this strict temperature profile over time to form a durable surface. During phases I and II, as the temperature rises from 30 to 110 degrees Celsius, free methylols begin to bond, transitioning the liquid resin into a flexible ether cross-linked network. Pushing into phases 3 and 4, between 110 and 170 degrees, forces the lock-in phase. The flexible network undergoes deep cross-linking, forming a highly rigid, insoluble thermoset. The margin for error here is near zero. Exceeding the specified press times or pushing temperatures too high triggers overcuring. The resulting chemical structure contracts violently, leading to excessive resin shrinkage, surface brittleness, and spiderweb microcracking. A perfectly cured resin surface serves as the final validation that the plate, pad, and substrate all maintain their required thermal and mechanical parameters throughout the cycle. Moving into the 2025 and 2026 manufacturing standards, managing this multi-layered stack is shifting out of human hands. The industry is adopting autonomous quality control systems. This data visualizes the computational efficiency of the incoming YOLO V8P's AI model. It achieves a 56.5% reduction in model size, drastically lowering processing requirements, while maintaining a 93.4% precision rate in identifying wood-based panel defects. Running in parallel is the PPO BoardNet system. It utilizes deep reinforcement learning to continuously scan for and catch specific microerrors, targeting dust spots, glue spots, scratches, sand leaks, and indentations. Deploying AI vision models transitions quality control from a reactive post-press inspection phase into an active real-time defect mitigation protocol. Maintenance is also advancing. Chemical cleaning is being replaced by laser ablation. This is a highly controlled dry process that completely vaporizes resin and oxide buildup without damaging the microscopic topography of the press plate. Manufacturers are also engineering the surface of the plate at the molecular level, applying exact 3 to 5 micron thick layers of silica or titanium dioxide nanocoatings directly onto the steel. These specific nanocoatings provide a Wolff-Wilborn scratch hardness rating of 8H or higher, while remaining structurally stable at temperatures exceeding 700 degrees Celsius. Alongside the tooling upgrades, chemical formulations are evolving to meet sustainability initiatives. New bio-based scavengers utilizing soy and hemp flowers are achieving up to a 70%